Now it's time to hear from a brilliant mind whose academic journey spans across continents and whose research is paving the way in the field of functional materials. Please join me in welcoming Professor K.R. Naveen, a newly appointed assistant professor in the Department of Polymer and Process Engineering at IIT Roorkee, who joined us just 3 days ago. He holds a master's degree from NIT Trichy and a PhD from Kyung-Hee University, South Korea. He has further enriched his academic experience through postdoctoral research at the University of Würzburg, Germany, and Kyoto University, Japan. His prolific work includes over 20 publications, and he is a proud recipient of 2 prestigious international fellowships, the Marie Curie Fellowship and the GSPS Postdoctoral Fellowship. His research interests include functional organic materials, narrowband polymers, boron chemistry, optoelectric devices, and thermally activated delayed fluorescence materials. With such a rich background and diverse expertise, we are honored to have him here with us today. Let's welcome Dr. Naveen on stage with a big round of applause.
Thank you. Good morning, everyone. Okay, so actually this is my first talk in IIT Roorkee. So I just joined 3 days back. So yet to I have to build the lab and my profile and everything here. So this is the just my future vision and whatever the work I have done previously. I just put very quick slides. As Professor Mishra also requested just yesterday only to do just 5 minutes talk. So thank you, Professor Mishra, for introducing. So my research topic will be Narrowband Luminescent Polymer Scaffolds towards the display industries. So this is the industry point of view because the conference is related to something related to industry. So mainly the semiconductor industry is growing in the India now. So among them, we need a lot of energy, and then energy and climate, both of the societal issues in the current 21st century. So we need to focus mainly to reduce the global warming and reduce the power consumption. So in order to achieve such kind of betterment, we need energy efficient lighting. So if you see in the room itself, we could see a lot of mobiles and laptops and several displays. Without light, you cannot live, right? So in such a way, one among the technology in the recent days has been developed. The name itself is organic light emitting diodes. So this is the light of the history of OLEDs, where it has started from the 1960. He was the Professor C.W. Tan who started the first OLED device from the Kodak company, which was in the Japan at the time. And then later on, this is the overall history. Until now, the people have developed several kind of displays. Even in the market now, we could see the even transparent displays also. And then one among the cost productive point of view, one among the best technology as of now also has been developed is developed by Professor Arachi, where the concept is TADF OLEDs. The TADF means thermally activated delayed fluorescence, where we don't use any metal kinds, which will be very low cost kind. So I'll discuss more detail about it. So let us see why we need to focus on such kind of display technology, why we need to have organic light emitting diodes, and how it will be implemented in the real lives. So this have the better solution processable also we can do it, and then it has the thin and transparent, and recently also as LG company has produced the 65 inches transparent OLEDs in the TVs. So it has the better quality of light compared to LCD and then previous display technologies. And then we can see the wide viewing angle which was impossible in the LCDs. Where I mean to say, you can see the OLED displays in different angles. the contrast and then visibility will be better. And then it can have the flexible and rollable, and then it will be having a very simple structure which can be eco-friendly in production. Then these are some of the technologies and then some of the market people have developed, like OLED displays in the mobiles, TVs, and then even in the cars also recent days. A lot of displays has been developed. And recently there is a new technology in the medical industry also. It has been used OLED bandages for photodynamic therapy, and even X-rays and all such kind of things need a lot of displays. So let us see how the OLED works, and then what is the basic mechanism, how the light is generated. This is the most important question people used to ask, how the light is coming from the OLED, right? So this is the OLED basic device architecture where we supply the voltage through the anode and cathode, where both the electrons and the holes are generated towards to the emissive layer, which was the center one. This is an emitter. All the other layers also are kinds of organic molecules, which will be even polymers also. Some of the polymers are notably used for the cathode and anode, and even electron transport and hole transport layers also. So one among the mainly, the emitter plays very important role, because from where the emission comes, right, from where the light is generated. So we'll be focusing mainly on how the emitter, what are the mechanisms in the emitters has been developed, and what kind of generation materials has been developed. So initially in the emitter, there will be two kinds of the excitons. I mean, the exciton will generate in the singlet and the triplet. This is like kinds of 25% assumption only. This is like 1:3 ratio, like 25% of the singlets and then 75% of the triplet excitons has been generated. So from this, the molecules has been developed. I mean, the generation of molecules, how in terms of the spins we understand, this is the condition. So in case of fast, as I mentioned, you can see here, always the singlet will be higher than the triplet due to the spin statistics rules. So this is the basic fluorescence molecules. Initially the first generation where this has been developed. Then followed by the second generation is phosphorescence, where the emission is coming from the triplet to the singlet. So here we need to use some metals to boost up the phosphorescence. But however, if we use the metals which is a highly cost, like iridium, platinum, such kind of things, if we use in the molecules, that will be very expensive. So in order to avoid that, the Professor Arashi has developed the TADF concept, where the 75% triplet excitons can be converted to the singlet excitons, and then 100% singlet excitons can decay back to the ground state by giving the fluorescence. So this is kinds of delayed emission, so we say that thermally activated delayed fluorescence. In order to achieve such kind of materials, we need to have very small energy gap between here, as I mentioned, this is the kinds of delta EST, singlet triplet energy gap. If we have very small energy gap, then we can assume that the triplet excitons can be converted to the singlet excitons. It's not 100% possible, but it is just an assumption. Okay. So, however, even the TADF concept has very excellent advantages, but however, in the real industry point of view, there are some drawbacks. Like if we want to achieve the proper color, usually the OLED displays use the filters to get the proper different kinds of colors, either blue, green, or red. But in order to avoid the color filters, if we have the narrowband materials, so this is the TADF concept, right? As I mentioned, you can see here. Usually the donor acceptor or donor acceptor donor are different kinds of the electron donating and electron withdrawing ability scores we used to use for the design the TADF molecules. But they usually separate the homo-LUMO, which is the molecular orbitals will be separated, right? So as you can see here, the red one indicates the LUMO, but the blue one indicates the HOMO, which is clearly separated, which indicates it can show the good ICT characteristics. Such kind of molecules usually shows the broad emission spectra. So in such kind of broad emission spectra, it will be a kinds of mixed colors, right? It is not the exact one color. It will be either blue green or green red, such kind of things. In order to avoid, Professor Hatakayama has developed a new concept where I have done my JSPS postdoc under him last year as well. So he developed the concept which is known as the MRTADF, where we use the atomical separation in the one molecules As you can see that the blue and green are alternatively aligned related to the molecular design. So this such kind of molecules usually reduce the vibronic coupling and then can have the extremely sharp peak where we don't need to use any color filters in displays. So that was the biggest advantage from this concept. So based on these concepts, I have done a lot of works based on that, developing a such kind of boron and nitrogen are some of the main group elements incorporations in all the designs, where we could be able to get the efficiency, high efficiencies in all the devices to over 30% around, and then get the proper different kinds of applications in OLEDs also. These are the molecules which we developed, which I developed basically, and then we try to publish in the big journals. So this was the another concept where Professor Adachi and we, in my PhD, Professor Adachi and we discussed to develop this concept. The concept name is hyperfluorescence, where we use in the device, this is the device architecture. As I mentioned, the anode and cathode basic one, and then followed by we have the different kinds of different layers, organic layers here. So we developed the hyperfluorescence by utilizing the TADF as a sensitizer, because that shows the broad emission spectra. And then we use this MRTADF molecule as the final dopant, which shows the narrowband, so that efficient singlet excitrons can be generated for the light emission. So among this, we get the around 40% efficiency because of the increasing the singlet excitrons. We identify the relevant reasons to get such efficiency. So this was the even highest until now. This was done almost 3-4 years back, but this was the work which is highest in efficiency and the stability point of view in blue LEDs even now. So because of this, we filed the patent also on this concept, and one interesting thing is based on this also there is a mobile also has been come out in the market already. The mobile is which was the Galaxy Z Fold 4, which have the foldable one from the concept of hyperfluorescence technology. So further in future, maybe we can plan even the rollable phone. Now we can see in the market some of the people are using the foldable phone, but we can try to have the rollable with the improvement of some polymers as well. So such kind of research is highly influenced towards to the energy, and which can even improve the society of the display technology. So this is the current status of the semiconductors. Like as you can see from the FCSP, like as you can see around 1 trillion market is also by 2030 has been increasing. Among this, our India is occupying 35% by the same 2030. So we could try to contribute for the semiconductor industries in the near future by developing the efficient materials and then efficient devices for that. So usually the people ask like, how do you do such kind of technology from the materials? We start from the materials like this initially and then go for the until the device final. Okay. And then this is the design strategies in the polymer point of view for the future developments. Until now only the 2D kind displays only we could see. The 3D displays also we'd like to develop in the future, where you can see 360 degrees view of the displays. That was my future vision. So I'd like to contribute on these kinds of concepts in the future. So thank you for your time.